Hello everyone, welcome to Dr. A classes for BTech students. This is lesson 3 on numerical exercises related to water balance. In today's lesson, we will explore the water balance concept, which is essential for analyzing hydrological systems. In this section, we will apply key principles through numerical exercises, reinforcing our grasp of inflow, outflows, and storage changes in real-world scenarios. Let us break down these calculations step by step to gain practical insights. First problem, a lake had water surface elevation of 103.200 meters above datum at the beginning of certain months. In that month, the lake received an average inflow of 6.0 meter cube per second from surface runoff sources. In the same period, the outflow from the lake had an average value of 6.5 meter cube per second. Further, in that month, the lake received a rainfall of 145 mm and evaporation from the lake surface was estimated as 6.10 centimeters. Write the water budget equation for the lake and calculate the water surface elevation of the lake at the end of the month. The average lake surface area can be taken as 5,000 hectares. Assume that there is no contribution to or from ground storage. Solution to problem 1. Explanation of the water balance numerical problem. The problem calculates the changes in water storage of a lake over a time interval, that is 1 month, based on inflow, outflow, precipitation, and evaporation. The equation governing the water balance is input volume minus output volume is equal to change in storage, or I delta T plus PA minus Q delta T plus EA is equal to change in storage, where delta T represents time interval, that is 1 month, I is average inflow rate in million meter cube per second, Q is average outflow rate in million meter cube per second, P is precipitation as a percentage, A is average surface area of the lake in square meters, E is evaporation as a percentage, delta S is change in storage volume in million meter cube. The time interval is given as 1 month, so delta T is equal to 30 into 24 into 60 into 60 is equal to 2.592 into 10 to the power 6 seconds. Inflow volume is calculated by multiplying inflow rate with time interval, which is equal to 6.0 meter cube per second into 2.592 million seconds equal to 15.552 million meter cube. Outflow volume is calculated by multiplying outflow rate with time interval, which is equal to 6.5 meter cube per second into 2.592 million seconds, that is equal to 16.848 million meter cube. The total surface area, that is 5,000 hectares, in converted into million square meters, which is equal to 50 million square meters. Precipitation is given as 14.5 centimeters over the surface area of the lake. So the total precipitation is calculated by multiplying the precipitation with the total surface area, which is equal to 14.5 by 100 meters into 50 million square meters, that is equal to 7.25 million meter cube. Evaporation is given as 6.1 centimeters over the same surface area. So the total evaporation is calculated by multiplying evaporation with the total surface area, that is equal to 6.10 divided by 100 meters into 50 million meter cube, that is equal to 3.05 million meter cube. Change in storage volume is calculated by adding inflow volume with the total precipitation minus outflow volume plus the total evaporation. So the value comes to 2.904 million meter cube. The change in elevation is calculated as follows. Since the lake's surface area is equal to 50 million square meters, that is equal to 50 into 10 to the power 6 square meters, the change in water level delta Z is equal to change in storage by the total surface area, that is equal to 2.904 into 10 to the power 6 by 50 into 10 to the power 6, that is equal to 0.058 meters or 5.8 centimeters. New water surface elevation. If the initial elevation is 103.200 meters, then the new elevation is equal to 103.200 plus 0.058, that is equal to 103.258 meters above the datum. The conclusion is the lake experiences a net positive change in storage, causing a rise in water level by 5.8 centimeters at the end of the month. This is due to the combined effects of inflow and precipitation being greater than outflow and evaporation. Problem 2. A small catchment of area 150 hectares received a rainfall of 10.5 centimeters in 90 minutes due to a storm. At the outlet of the catchment, the stream draining the catchment was dry before the storm and experienced a runoff lasting for 10 hours with an average discharge of 1.5 meter cube per second. The stream was again dry after the runoff event. So, what is the amount of water which was not available to run off due to combined effect of infiltration, evaporation and transpiration? B. What is the ratio of runoff to precipitation? Solution to problem 2. Water budget equation and runoff calculation. Now we will discuss the water budget equation and its application in determining runoff from a catchment. This concept is fundamental in hydrology, helping us analyze the balance between precipitation, infiltration, evaporation, and runoff. Water budget equation. The water budget equation for a catchment over a given time interval is expressed as R is equal to P minus L, where R represents runoff, that is outflow volume at the catchment outlet. P represents precipitation, that is input to the system. L is losses due to infiltration, evaporation, transpiration, and surface storage. Problem statement. A small catchment of 150 hectares received 10.5 centimeters of rainfall over 90 minutes due to a storm. Before the storm, the stream draining the catchment was dry. After the rainfall event, the stream experienced runoff lasting for 10 hours with an average discharge of 1.5 meter cube per second. Once the runoff event ended, the stream was again dry. So we need to determine A. The amount of water not ever available for runoff due to the combined effects of infiltration, evaporation and transpiration. B. The ratio of runoff to precipitation. The steps 1 is calculating precipitation input, that is P. Precipitation input is given by P is equal to rainfall depth into catchment area. So the catchment area is 150 into 100 into 100, that is multiplied with 10.5 by 100, that is precipitation in meters, which comes to 157500 meter cube. Step 2, calculating runoff volume, that is R. Runoff is the total outflow volume at the catchment outlet given a flow rate of 1.5 meter cube per second. The total runoff volume over 10 hours is R is equal to flow rate into total time, that is R is equal to 1.5 into 10 into 60 into 60, that comes to 54000 meter cube. Step 3, calculating losses, that is L. Losses include infiltration, evaporation and storage within the catchment. So the L is equal to P minus R. So the L is 157500 minus 54000, that is 103500 meter cube. Step 4, calculating runoff coefficient. The runoff coefficient is the ratio of runoff to precipitation. If the runoff coefficient is C, is therefore equal to R by P. R is runoff, P is precipitation, that is equal to 54000 by 157500, that is equal to 0.343. Conclusion. The runoff coefficient of 0.343 indicates that approximately 34.3% of the total precipitation contributes to runoff, while the remaining 65.7% is lost due to infiltration, evaporation, and storage. Understanding these calculations is crucial for water resource management, flood prediction, and sustainable hydrological planning. Problem 3. A catchment area of 140 square kilometer received 120 centimeters of rainfall in a year. At the outlet of the catchment, the flow in the stream draining the catchment was found to have an average rate of 2.0 meter cube per second for 3 months, 3.0 meter cube per second for 6 months, and 5.0 meter cube per second for next 3 months. So, what is the runoff coefficient of the catchment? Second, if the afforestation of the catchment reduces the runoff coefficient to 0.50, what is the increase in the abstraction from the precipitation due to infiltration, evaporation and transpiration for the same annual rainfall of 120 centimeters? Solution to the problem. Here is another example where we will use the water budget equation to figure out runoff. Problem statement. A catchment area of 140 square kilometer received 120 centimeters of rainfall in a year. At the outlet of the catchment, the stream draining the catchment exhibited an average flow rate of 2.0 meter cube per second for 3 months, 3.0 meter cube per second for 6 months, 5.0 meter cube per second for 3 months. So we need to determine the runoff coefficient of the catchment. Second, if the forestation reduces the runoff coefficient to 0.50, what is the increase in abstraction from precipitation due to infiltration, evaporation and transpiration given the same annual rainfall of 120 centimeters? Step 1. Calculate precipitation input, that is P. Precipitation input is given by P is equal to rainfall depth into catchment area. The rainfall depth is 120 by 100 in meters. into 140 into 10 to the power 6 square meters is equal to 168 into 10 to the power 6 meter cube is the total precipitation input. Step 2. Calculate runoff volume, that is R. The total runoff volume is obtained from the stream flow rates over different time periods. Runoff in first 3 months, in next 6 months and in next 3 months respectively will be runoff event 1 is equal to 2.0 into 3 months into 30 days into 24 hours into 3600 seconds is equal to 15.552 into 10 to the power 6. Runoff event 2 is equal to 3.0 into 6 months into 30 days into 24 hours into 3600 seconds, that is equal to 46.656 into 10 to the power 6. Runoff event 3 is equal to 5 into 3 months into 30 days into 24 hours into 3600 seconds is equal to 38.88 into 10 to the power 6. Therefore, the total runoff volume R is equal to runoff event 1 plus runoff event 2 plus runoff event 3, that is equal to 101.088 into 10 to the power 6 meter cube. Step 3. Runoff coefficient. The runoff coefficient is given by C, which is equal to total runoff volume divided by total input precipitation, that is equal to 101.088 into 10 to the power 6 by 168 into 10 to the power 6, that is equal to 0.602. Step 4. Calculate increased abstraction due to afforestation. If afforestation reduces the runoff coefficient to 0.50, then the new runoff volume, that is R dash, is 0.50 into 168 into 10 to the power 6, that is equal to 84 into 10 to the power 6 meter cube. Increase in abstraction losses due to infiltration, evaporation and transpiration. So the change in loss is equal to 101.088 into 10 to the power 6 minus 84 into 10 to the power 6, which is equal to 17.088 into 10 to the power 6 meter cube. So the conclusion is the initial runoff coefficient is 0.602. Afforestation reduces the runoff coefficient to 0.50, resulting in an additional abstraction of 17.088 million cubic meters due to increased infiltration, evaporation, and transpiration. This demonstrates the impact of land use changes on catchment hydrology, which is critical for sustainable water resource management. Self-assessment numerical problems. At the end of the presentation, these are self-assessment numerical problems. Carefully go through each question, solve them based on your understanding of the topic, and review any concept you are unsure about. The questions are 2.5 centimeters of rain per day over an area of 200 square kilometers is equivalent to average rate of input of how many cubic meters per second of water to that area. Second is estimate the constant rate of withdrawal from a 1375 hectares reservoir in a month of days during which the reservoir level dropped by 0.775 meters in spite of an average inflow into the reservoir of 0.5 million meter cube per day. During the month, the average seepage from the reservoir was 2.5 centimeters. The total precipitation on the reservoir was 18.5 centimeters and the total evaporation was 9.5 centimeters. The third question is, a river reach had a flood wave passing through it. At a given instant, the storage of water in the reach was estimated as 15.5 hectare meter. What would be the storage in the reach after an interval of 3 hours if the average inflow and outflow during the time period are 142 meter cube per second and 10.6 meter cube per second respectively? Thanks for joining this lesson on engineering hydrology today. I hope you found the presentation informative and helpful. So don't forget to like and subscribe the channel Dr. A Classes for more engaging lessons on core civil engineering subjects. You can also write to me for any further clarifications or questions. Thank you.